Okay, don't go too far, Mike, because you're part of the next presentation as well. So I don't need to reintroduce Mike here, but I'd like to introduce our second newest board member at Sustainable Buildings Canada, Michelle Xuereb, a senior associate in sustainability strategy at Quadrangle Architect. She'll join Mike Williams in presenting on designing for future weather. So, take care, guys.
Okay.
Sorry, Michelle.
Oh, you got the
Sorry.
keys. Okay, originally mine was supposed to follow Mike, so just bear with us here, because he was going to talk about it from the perspective of the engineer, and then I was going to get up and talk about it from the perspective of the architect. So I'm talking about designing for future weather, and this is the path we're going to take for this discussion. So mitigate, adapt, know the facts, address the risk, and then a few takeaways of what you can walk away with today of tangible things that you can do. So climate change, we all know the big bad word. It's part of why we're here. Really, there's kind of two paths, two things that we've been talking about within the community. One of them that we've been talking about for a really long time is climate change mitigation. So how do we slow things down? How do we reduce carbon? How do we mitigate? We now know that the climate has changed, and this is coming from, it would have played off Mike's. And now what we're looking at is we're looking for ways to adapt. So we're now doing these two things at the same time. So you're trying to mitigate and you're trying to adapt. And what I find interesting is that the solutions for both of those things are really the same thing. They're really about passive design. And once again, you're going to see the recurring theme around building envelope and thinking about the building in a passive way. So we have to start by knowing the facts. Luckily, there's a lot of smart people out there. And through the Transform TO project, Toronto's put together this great graphic that talks about where we expect our climate to be going kind of by 2040, 2050. And what we see from this is increasing daily temperatures. We see more of those days, and we see more of those days strung together into heat waves, so more extreme heat events. The other thing we see is a rise in our daily maximum precipitation. What that means is a lot of what we saw this summer, which is a lot of rain at once, which, with all the paved surfaces that we have, can be a challenge for us to deal with. So out of this, we know that the issues that we are contending with are things like flooding, which, once again, we saw this summer, extreme heat. And with those two things, what we often have is we have power outages. And so you're dealing with two, possibly three of these factors at the same time. So then what can we do as designers to address the risk? If you think about the way we've been trained to think in terms of life safety thinking, the Ontario Building Code is designed around the premise of evacuation because our biggest threat was fire. If you talk to the insurance people these days, the claims are not coming from that. They're not coming from fire anymore. But our codes are designed around this. You've got fire separations, you've got time it takes for a person to evacuate. An operating room is going to be different because you might have to close the patient and then move them. Different ideas about air movement, smoke movement through a building. So that was one way. So our codes are rooted in that. But when we talk about climate change adaptation, part of what we're going to have to start thinking about is the concept of sheltering in place. So if you look at what happened in Florida last month, you watched the horizontal evacuation, you watched gas stations emptying out, you watched congested freeways and people trying to leave the place. It might have been a very different situation had those places been designed understanding the risks and understanding how they could stay in their place. So how do you do that? So there's this concept, and I think it's been raised by all panelists at this point, this concept of passive survivability. So when we're thinking about our buildings, it's really about our building's ability to maintain support so that you're able to stay inside it during the absence of power, fuel, water, And how do we do that? And how do we create a building that reflects passive survivability? So let's look at each of the risks. So starting with flooding, again, lots of water falling at once. So I went to the TRCA, again, a bunch of smart people, maps, flood maps. How do you read them? I'm looking at them, I'm thinking, okay, this is about basement flooding. There were several maps, I just pulled one. And then I thought, well, what do I need to know as an architect and as a designer about this? And what is this telling me exactly? So I went to a building section. So what is that line? How high is the water going to go and how do we know? And where's the water coming from? So we've got water from two things. You've got your waterways overflowing, but you've also got our infrastructure backing up. And I know that there's some efforts underway to continue with the mapping, and I'd encourage that. So we can start to think about some of these ideas. So the question that I have to all those smart people dealing with water is, what's that line? Where's the limit that we need to be working to? And then you can start thinking about the concepts. Right now, the inexpensive space is the underground space. You've got your mechanical and your electrical systems. Often your services are coming in down low, and so we're putting our electrical rooms, our high voltage transformer rooms down in the basement. It's probably not the optimal place for them to be in the event of excessive water. So how do we start the conversation about pulling these things up and over that flood line? Backflow prevention, again, not a new technology. In new buildings, that's just what you do as a matter of course. It's the old buildings, it's the existing buildings. It's about retrofitting and making sure that we're protected. And then we've got the type of materials that we use. So starting to think about where that line is and what kind of materials you put down below it. I know when they did the Don Valley Brickworks, there was a lot of thought put into the height of the electrical outlets, what kinds of materials were there that could weather, because they went in there knowing that this area was subject to flooding, and that changes the way you think in terms of design and materiality. Then we can talk about extreme heat. Again, hotter days, more of them strung together, and power outages happening at the same time. So we come to this concept of thermal resilience. Again, I think it's one of the concepts of passive survivability. So again, it's the building's ability to maintain its temperature. We've talked a lot about window wall, a lot about glass. We know that heat is actually going to become one of our issues. We've been talking so much, you looked at some of the graphs that Birgit put up there, and the heating load. We think a lot about the heating load, but one of the other issues is going to be the concern of buildings overheating, and Mike's going to give you some good graphics on that. And so the idea is that what happens when you unplug the building? And again, through some of the studies that the city put together to put together their zero emissions framework, they did some actual energy modeling that looked at what happens when you unplug the building for 72 hours. Because in that any kind of an event that you have to have your own ability to react to it while the city is taking care of things, fixing things, getting things back online. And there's a period of time. So they looked at sort of a 72-hour period and could a building maintain its temperature. Really, in terms of solutions, architectural solutions, these are the most basic of diagrams. This is taking us back to first principles of design. It's about thinking about orientation. We know in our climate and where we're located that the place where we tend to overheat is really on the west and on the south. On the south, we can control temperatures. On the west, it's much more difficult, so minimizing that edge. Again, window to wall ratio, very common theme here. Bringing those numbers, thinking about more of a punched window approach instead of all glass. Again, multi-unit residential, we do a lot of it. Thinking about where we put these things. So balconies. Balconies to me make a lot of sense on the south because they also provide the ability to passively shade. On the west, balconies don't do that much because your sun is coming in at a low sun angle, setting sun, hot day. Really, you want vertical elements. If you put vertical elements on your balconies, it's quite likely they'll get value engineered. So put it into the design from the first instance. Look at insetting your balconies. It's just a kind of a simple solution. Operable windows. Seems to, that it would just go without saying. Every room, thinking about how to naturally ventilate. Walls, not window wall, again, common theme. You know, the ability to actually put some thermal value into your opaque assemblies. Best possible windows that your budget can afford. And more, I think we're going to start to have the conversation about triple glazed windows. I know nobody wants to talk about it here in terms of budgets, but that's the direction that we're going. And then there's this last piece, and this is about opportunities for social connection. In an emergency event, the people that do the best are the people that have social connections around them. So the neighbors that are integrated, the people that know one another. So in terms of design, and this has kind of come up in a few of the presentations again this morning, it's really about creating opportunities for people to know one another. I heard the Chief Resilience Officer speak last week, Elliot Chappelle, and he was talking about the fact that we're one of the fastest growing cities in the world. 569 towers going through the municipal process right now. That's a lot. That's a lot of new people. That's a lot of new neighbors, a lot of people that don't know one another, and a lot of opportunity to start to think about neighborhoods, vertical neighborhoods. So how do you start to think about that? Instead of just thinking about the ground plane, we really need to start to think about our towers, spreading the amenity spaces across it, doing things like lovable stairs, a stair that is not just about evacuation, something that you think about that somebody might want to actually use and they're not afraid of getting hurt or getting locked out at the bottom, but something that is usable and that encourages movement. Because at the end of the day, it's your neighbors that are going to get you through those first few days. And then there's the area of refuge. Again, this is something that they talk about within the building code. Area of refuge is something that you think about if you think about a hospital and moving stretchers to one location so that people are safe until someone can get to them, or a balcony where you wheel someone out and you alert people that they're there. But what an area of refuge could be about in this instance, where we're talking about it in extreme heat, is a place to go and to cool down, a place to go and to charge your communication device, a place to plug in your medicine, to a fridge where you can cool your medicine. So these kinds of things, and buildings kind of having these plans so that they can get through those first few days. So what can you do? So the takeaways. So number one, and again, a common theme, is just understanding and explaining your local climate change risks and these strategies to your clients. I've been very Toronto-centric in my presentation, and it's going to be very different somewhere else where, forest fire is your issue or hurricane. Second, prioritize passive design principles and that reduce thermal demand. And again, this is Toronto-specific. Mitigating flood, anticipating power outages. So thinking about those things, not just going back to your business as usual approach to locating. And then support the use of climate future scenarios during the design process. And again, this would have been more effective if it was after Mike. But we're going to talk about weather files and understanding, as an architect, the energy model. Understanding it well enough that you can have a discussion with your energy modeler and not just saying, I got the energy model, we passed, check. Because there are inputs in there that are critical to the success of the building. And one of those elements is what weather files are being used. And then, of course, create opportunities for social connection within your design. And finally, just as citizen, get to know your neighbors. Thank you.
All right, thanks, Michelle. So I was going to introduce Michelle, but now I don't need to. So we can just move right on beyond this slide. No, I'm going to talk about designing for weather futures. RWDI has been embedded in understanding microclimates around buildings since we were founded in 1972, starting looking at snow loading around buildings, moving into wind studies around buildings. And so we're deeply entrenched in trying to understand weather and how it interacts and causes the built environment to respond in different ways. So this is a graph of heating degree days. Heating degree days are an indication of when a building is going to need heat to remain comfortable inside. And so if there's more heating degree days, that means it's colder outside. You can see, and so this is historic data from 1950 up to 2014 from Pearson Airport. And you can see a definite trend of those heating degree days decreasing from climate zone 6 all the way down into climate zone 5. So climate zones are what ASHRAE uses to define or suggest, and in some cases require, various building characteristics. So in a higher climate zone, you'd be required to provide more insulation. In lower climate zones, you'd be looking at higher solar heat gain coefficients, things like that. So what I often say, and as Michelle was going to tie in, this is a funny back and forth, but the climate's really changed, and I think we need to change the tense of the conversation. Someone was actually recently asking me if I think there's any validity in these climate change skeptics, and I said, you can go and get the data yourself from an airport, and there is a change in the trend, and that is historic data. No one can argue that the climate has changed. You may be able to argue why that's happening, maybe, I don't think so, but the fact is it's changing, and we now need to start to do things differently. So this idea of thinking about, well, so what? So the climate's changed. What do we do now? How does that impact the different design decisions that we make? We do a lot of energy modeling at RWDI, and so sort of thinking about that question, what is the weather file that we're using for our energy models? The weather file that you select is one of the largest drivers of energy performance in a building, which sort of makes intuitive sense, but I don't think we often stop and pause and say, well, what is the weather input? What does it represent? And so if you look at almost every energy simulation that's completed in Ontario and probably Canada, they use a weather file that's called a CWEC. And so a CWEC represents a typical meteorological year for the period of 1950 to 1985. So a typical meteorological year, or a TMY, selects the most typical month from the most typical month for that period. So the weather file may end up being generated of January 1955, February from 1984, March from 1983, whatever happens to be that most typical month, you collect those 12 typical months together, and that becomes your weather file that you then use for your simulations. So it's trying to represent the typical weather over that period of time. And so by that red box, you can probably see the problem that I'm trying to point out here, that we're using weather files that don't even represent the right climate zone. So we did some digging, and we found a private organization called White Box Technologies, and they had created a series of weather files that represented the weather period from 2000 to 2014. So they made the TMYs and converted them into, this is an engineer presentation, it's more acronyms, into EPWs, which we were then able to plug into our energy simulations. But this is now a weather file that better represents today's climate. But I think not only has the climate changed, I mean, you can see a very clear trend in this data that it is still changing. And so Michelle referenced this Toronto Future Weather and Climate Driver study that was not conducted by the city, but the city commissioned this study in 2011, and that infographic that Michelle showed are some of the outputs from this study. So essentially, what the study entailed was a large weather research forecast model, or a WRF, if you want the acronym, and the engineers refer to it as a WRF. And what a WRF is basically a macro-scale computational fluid dynamic, CFD, simulation over a vast region. And so it represents science's best ability to try to predict all these interactive elements of climate, and then you run this big computational fluid dynamic simulation into the future to try to predict what the future weather is going to be like. And so that's what this study did, and it looked at the period from 2040 to 2049. So we got in touch with the city, and they gave us that hourly data from 2040 to 2049. We did some processing. I should make this into a test. And we made a TMY, which is typical meteorological year, and plotted that onto our graph. And so you can see what the study is telling us is that we're on our way to ASHRAE Climate Zone 4. And so this is down into Washington, D.C. I like to joke a lot, but this graph, it's scary, right? Like 2040 is 23 years away. That's not that far. The buildings we're building today are going to be operating in 2040. Are they going to be ready are they going to be able to meet up with the cooling demands for these new climate realities? And I think perhaps you can argue, well, this WRF simulation, all this hokey pokey CFD, but look at the historic trend. If you just took a linear trend through that, it's not that far off of what this computational fluid dynamics simulation is saying. This is a graph that we've started to call in our office the graph, because I think it's a very powerful message about what's happening to the climate and what may be happening to the climate. So all these slides are going to be available. I've actually seen this slide start to pop up in some others' presentations. You're more than welcome to do so. I really want to see this kind of study and this kind of knowledge being disseminated. So to take this a level further, we took these 3 climate files, the Seebeck, the CN 2014, and what we're calling the 2040s, and we plugged them into an archetype energy model. So this is a high-rise MERB located in downtown Toronto with market normal construction. And so we took all of those simulation files and we plugged them in. And one of the outputs that we looked at was the energy use intensity. So lower energy use intensity is a good thing. So you can see in the 2040s, climate change has a good news story. We have a decreased energy use intensity. Now, this is largely driven by the fact that we can cool more efficiently than we can heat. And so when there's more demand for cooling and the chillers work at those higher coefficient of performance, or COPs, than heating does, we see a decrease in the energy use intensity. I think it's interesting to look at this CWEC versus the CN 2014 and look at the percent difference between the two. Maybe 4% doesn't look significant, but think about 4% from the context that Toronto Green Standard Tier 1 requires a 15% reduction, Tier 2 requires a 25% reduction, so that's a 10% delta. So 4% is about halfway to what can be hundreds of thousands of dollars in development charge refunds just for changing your weather file. So this is a very important fundamental input to energy simulations, and I think we really need to make sure we stop and think, what are we feeding into these energy simulations, and at least being conscious of it. But perhaps the more concerning metric is looking at unmet cooling hours. So an unmet cooling hour is when there is at least 1 hour of the 8,760 hours of the year that the building system cannot meet up with the demand for cooling. And so the 2040s simulation found 728 hours. If we considered that all of those hours happened during occupied times of the building, that's 3 months that the occupants of this building are not going to be comfortable. I think you're going to get some tenant complaints. This is going to be a problem, and I'm concerned that this may be one of the ssolutions. I was recently in Hong Kong, and this is a popular design mode, I guess. I don't know. I think we need to start thinking about adaptable design, thinking about these future climate potential realities. How could we build adaptability into our buildings? Could we create a structural system so that we could easily clip on an external shading device into the future if the building demanded that? I think all of these future scenarios are not certain realities, and so maybe we can't afford or we can't fully design for them today, but I think we need to start thinking about how we can adapt, or this is how we're going to have to adapt. So an asterisk on this study, very recently a NRC-funded study produced a new set of the Seebeck files. So these are now publicly available on this website, climate.onebuilding.org. And so these Seebeck files represent a weather period from 1985 up to 2014. They're calling them the Seebeck 2016. Download these, they're free. This is what you should be using in your energy simulations. Don't be lazy and just use the one that's still sitting on your desktop. It's an easy upgrade to make. It's a really important input consideration into your energy simulations. So I think this is a great update. So let's make sure that this is how we're doing our energy simulations moving forward. So just a couple of the takeaways. I think this idea question, what is that weather file that's being utilized in an energy model? There's some folks here who I know are energy simulators, so you'll be posing that question of yourself. I also see a lot of architects, developers that are often procuring energy simulations. So pose and prod with these kind of questions. It's not that hard once you have the energy model set up to plug in a different weather file. So why not play around with some of these different climate future weather scenarios and start to have a quantified understanding of what these impacts could be, and then start to do some integrative design work to think about how we can adapt the design potentially in the future to respond to it. So as we showed, the climate is changing, and I think this idea of sustainability, as Michelle alluded to, has gone from just being about trying to mitigate the impacts of the built environment to now having to adapt to new climate realities. And so it's now a two-pronged discussion talking about continued mitigation, but now having to adapt to new climate norms, and I think an ever-changing future. So this was going to be the tie-in to Michelle, but I think it is interesting how it all relates back to these passive design solutions that are going to help to reduce thermal energy demands in buildings. If you can reduce those thermal energy demands, then you are resilient to whether it's increased heating or increased cooling into the future. And so these passive design solutions can help be one of those adaptive design considerations. So that is the end of the talk. Thank you very much. And I think Larry's going to come up.
Well, thank you very much, everybody. Some brilliant insights there from some of our best weather specialists especially. So thank you very much. We are early. So with that, we have the opportunity to have a fulsome Q&A session here. Do we have any questions for our panelists? Right over here.
Something that was missing was a discussion of equity in the metrics that you're using. When you're using energy use intensity or kilograms, or like kilowatt hours per square meter per year, or you're using carbon, kilograms of carbon per square meter per year, what happens when you have a situation where you have a MURB and you've got 600 square foot units and you've got a luxury building with 3,000 square foot units, 5 times the floor area? It's a lot easier in a 3,000 square foot unit to meet an energy use intensity or carbon target. Should we not be introducing an additional metric that reflects occupancy and intensity of use of our buildings?
Yes.
Anyone want to elaborate on that firm yes?
I think, like, to further to my yes, I think there's also a discussion around if it's really the absolute amount of carbon. It's not the intensity, it's the big carbon players. And maybe it's not just because they have big suites, but maybe they're an intensive lab, and so they have a high carbon footprint. That's where we need to be investing the dollars to reduce carbon emissions. So I agree, and for me, it's really on the carbon metric that I don't think that looking at intensity is the sole correct metric. I think it needs to be absolute as well.
And just the thing that I would add to that is one of the things I like about the new proposal for the TGS is that there's multiple metrics, and you might find you do well in one and not so well in the other. And it's encouraging the right way to design our buildings, and that's the direction I hope we'll end up taking. We'll see when it goes to council.
I'm going to go back and forth again.
I have a quick question for Mike Williams. That 728 hours of unmet cooling, that's compared to what today? And is it for a building with no cooling system, or one that's just sized for present-day peaks that it can then no longer meet in the 2040s?
Yep, that's a good question. So we decided to leave the cooling plant the same size, and so the cooling plant is still at the sized for today's weather. So, and we thought that would be, you're alluding to something that's interesting, that buildings do go through life cycles, and so perhaps the building system would have been upgraded prior to reaching that 2040 failing point. But we thought it would be interesting to say, okay, so the building system remains the same, what happens? But you're right, there might be an opportunity to increase the size of the cooling plant and reduce those unmet cooling hours.
Oh, okay, so in other words, it's 0 today because it's sized for today's cooling loads, and then if you leave it the same, you get the 728 unmet hours.
Yep, that was the study. And I think we're actually doing some work with the city trying to forecast out some of their building condition assessments and what they should be doing into the future based on potential future weather patterns. And so trying to incorporate future thinking into long-term capital planning. And so I think what this study could say is that when you do that next upgrade, you should reconsider the weather, not just like for like.
Okay, thank you.
Steve?
Thanks, Mike. You're working with some pretty high-powered people. Congratulations. This stuff is all close to my heart. One observation is that Environment Canada now has 3 30-year sets of data from 1960 on the Climate Normals website. And so you can go and look at that data and you know, see where the temperature is going. One of the interesting things, and I'm raising this because the Institute for Catastrophic Loss Protection has produced documentation suggesting that as the climate gets warmer, everything just moves up. When if you look at those 3 sets of data, up until last month, most of the highs and lows were set in the 40s, with some miscellaneous things showing up in the 70s and 80s. And the mean has moved. So the distribution is no longer normal. It's tilted towards the hot side in terms of the mean, but the highs and lows are stable. Now that may change, of course, but that's where it is now. So it's important to get the update for the Seebeck Files. It's important to move along with what those averages do as they change. So thanks for that reference. And in terms of other people looking at doing what Diamond & Schmidt has done, it's not hard. I mean, Diamond & Schmidt now has a wonderful portfolio, and they've got enough statistical evidence to start using that as a design tool. But you've got to start somewhere, so just put your buildings on a spreadsheet and get on with it. I mean, Portfolio Manager will help you with making those EUI metrics. There's a lot of ways of getting the information on, but it's at your fingertips, so please use it.
Thanks, Stephen. David?
Thank you. It looks like an very interesting project where you're comparing all the different buildings of the portfolio. But what you were saying was that this is what you're comparing is the building models. And my understanding is there's not necessarily a strong correlation between actual performance and the modeling. And so I'm just curious to hear your comment on that observation.
That's a very good observation and accurate. We as designers are working with the models. So that is the basically the parameters with it, that are helping to inform our design. And what I've noticed as we've been working on this ecometrics data bank is that modeling is also changing. Like modeling is not a perfect science. It's sort of art and science, and it probably has several failings, and that entire community has to get together and figure out how to make their modeling more accurate, because that is what we in the design process are using as our tool. That's what we submit to the city, what we submit to LEED, what we submit to all sorts of governing bodies or targeting systems until we move into a phase of real data informing things and have that feedback loop. And I think we have the basis for that feedback loop now, and Mike was able to share that quite clearly, how you take this mind-boggling data, written data, and transform it into something visually accessible. But still, I don't know that we're going to get away from models being our, what we work with as the design community during the design phases of a project. Does that answer your?
Yeah, I mean,
question?
the other observation, of course, is that the best way to improve your modeling is to compare it with actuals and close that loop. So if we're doing that, then that's going to improve the modeling without question.
Yeah.
We're also fortunate that mandatory energy reporting is now in place for the public sector, and it's now coming for the private sector as of this year for large buildings, and then it phases in over the next 5 years. So it's really hard for us to get that energy data from many of our clients, but now they can't say no anymore. So I think there's going to be a great opportunity to close this loop with all this new data.
So you have more fun ahead of you.
Tristan was twitching in his seat there on that, so.
So I just wanted to address from a modeling practitioner's point of view this concept of the performance gap, because it gets kicked around a lot. And really comparing modeled data that is really capturing your first step into the world as a design. I've often heard it said that in the design community, we make good recipes, we don't actually bake the cake. You know, there's issues of constructability, how the building was commissioned, how it's being run, and a lot of those things will very much influence what those actuals are, but could never really be captured in the model. And it's not that the model's lacking accuracy, it's just there to represent the design on that day zero or day final of completion of the design. And really, it's one of the reasons why energy modeling is best used as a comparator between, you know, what if we did this, what if we did that? Because all of that noise that can happen when you actually put real occupants in a building can get muted out and just start comparing the like-for-like changes between two things.
Just quickly, sorry, 2 seconds, is that even post-occupancy measurements and metrics don't necessarily always reflect the intended design, because what happens is when the occupants actually take over the space, we've seen evidence of people completely either misusing or abusing the systems, and you think that you can track a correlation between norm and non-norm, but it completely throws the data for a loop. So you end up kind of trying to rationalize, and so this is why we're trying to look at ways to develop patterns and read the patterns and see what those patterns are, so that we can actually feed that back in at the beginning of the process.
We still have a couple of minutes, so I'll take the last two questions.
Okay. Oh, hi, we're going to pick on Mike again, sorry. I thought you made a great point about how the climate is changing, and designers in this room probably need to take that into account as they model forward. But I was just curious about whether, like, I think what you were talking about was very specific to Toronto, was it not?
Yep.
Yeah, because, I mean, I think you also agree that Toronto probably has the biggest heat island effect issue probably in Canada. So if you're designing for buildings in London or Kitchener or other places down here, you know, you'd have to take that into account as well, right? And does the heat island effect skew with the data that you presented to us?
That's a good question. I guess maybe not, because what the historic data we looked at came from Pearson Airport, and so I don't know that we would see the skewing of the heat island effect. So I would say that's a variable in these energy simulations that we don't currently account for perhaps well enough. I don't know, Tristan, what do you think?
There's actually been some fairly interesting work done on this by Drew Crawley and Christoph Reinhardt. Both have focused on this. One's a professor at MIT, the other, Drew's just a godfather of energy modeling for Department of Energy, looking at adapting these weather files for specific urban climates and how to get a scale in them that approximates the heat island effect. Often because, you know, Pearson's a little bit of a different case because it's still surrounded by urbanized area, but oftentimes because weather stations are at airports or airfields that are outside of a downtown core, there has been some look at, all right, well, if I'm, you know, designing a building in the financial district, how can I tweak this weather file to actually start capturing, the heat experience that we're having in downtowns in July instead of what we're having, you know, at an airfield outside the city limits. So it's being kicked around and looked at, but I haven't found any really good, reliable set of heat island adjusted weather files for various locations.
Okay, cheers.
That's a good question.
One more?
My question is also for Mike, but before that, I just wanted to make a comment about an earlier question. In Switzerland, they actually have the 2,000 watt society, which I think is really interesting, because if you think about, okay, so if you have one person, all the energy they use in 1 year has to be below 2,000 watts. And if you start adding up how much energy we actually use in just 1 month with our Canadian lifestyle, it's kind of crazy. But I think that's an interesting thing if you want to think really visionary long term, to kind of move towards individual energy use, not just buildings, but in every aspect. But my question is, you know, you suggested maybe we should start using more of the future weather Files. And, if you have some energy modelers using the Seebeck and TMY from historical data, and some are using future data sets, you're going to have the client getting very contradictory information. And I wonder if this is something that needs to happen at the policy level, which is something, in Germany and Switzerland, they actually have validated future weather data sets. And of course, you have to have the confirmation for the current or historical data sets, but you can also show, okay, we can also meet the overheating conditions for future data sets. And that's something that's, common practice, you have to do it. So my question is, how can we move towards that to have policy actually require this from the energy practitioners so that we're not getting contradictory information there?
So there are policy changes that are happening. So there's a new energy modeling framework that's coming out in the City of Toronto, and it thankfully says that you have to use the CWEC weather file, and I'm hoping everyone interprets that to mean that you have to use the CWEC 2016 weather file, and I think maybe a point of clarification in that guide would be worthwhile. I think in terms of doing some of these future weather studies, we're trying to do some research like this that was actually funded by Sustainable Buildings Canada, and letting people know that these things can be done, and hopefully some people in the crowd see this and think it's interesting, and maybe the research gets expanded, and we can create these TMYs, the test anyway, typical meteorological years for a number of different locations, and I think that would be a powerful outcome.
Well, I'd like to thank our panel here, not only for their excellent presentations, but for sticking to the clock and giving our audience the opportunity to make some inquiries. I'll just ask you to hold your seats for a minute while I make a couple of quick announcements. Before we break for lunch, a couple of announcements. First, we're very pleased to welcome SBC's annual bursary winners to today's Green Building Festival. Each year, SBC bursaries support 3 post-secondary students in the pursuit of their educational goals. This year, all SBC bursary recipients were female university STEM students, science, technology, and engineering, and math. A couple of them are here today, and we'd like to acknowledge their exceptional academic performance in their studies that prepare them to work here in the sustainable buildings sector. Could I ask Christina Asmelios and Sarah Lukacic to please stand up? Are you ladies in the crowd here? Don't be shy. And I'd also like to recognize Haley Cormick, who unfortunately isn't able to attend because she's working in London, England now. So also, please take a few moments to check out our student posters. They're located over here. These posters represent the work of our most promising students and their academic pursuits. Stop by their presentations to meet tomorrow's emerging sustainability stars. Finally, SAB Magazine's Green Building Awards recognize excellence in the design and execution of Canadian residential and non-residential buildings of all types. Thanks to our festival partner, SAB Magazine, the winning projects are also on display, and they're definitely worth investigating. Finally, a special thanks to our lunch sponsors, co-sponsored by Outside In Design and Build and Sage Living Toronto. I'd like to invite you all now to enjoy a healthy lunch, and we'll see you back here at 12:50.